Hi everyone, I am Chloé Rouillet, a PhD student from the University of Copenhagen, and I'm glad to present the work that we did together with my supervisor, Yevgeny Seldin. I will start by an introduction to place our problem setting in a more general context, and I will then present our work. Let's start with the introduction. Multi-arm bandits is a central framework for studying the exploration and exploitation trade-off. In the multi-arm bandit game, a player repeatedly chooses actions, also known as arms, from a set of K arms, and then observes and suffers the loss of that arm. That loss can then be used to improve the future choices of arm, but also adds to the cumulative loss, which the player aims to minimize. We study a variation of the multi-arm bandits problem, where the player is allowed to choose two arms at each round, which can be identical. Then the player blindly suffers the loss of one arm and observes without suffering the loss of the second one. We can see that this variation is a relaxation of the classic multi-arm bandits problem. This problem setting has been studied by Avner and al. In 2012. However, there has been recent improvements in the analysis of classic multi-arm bandits that led the results of Avner and al. Not to be as competitive as they used to be. We consider the work of Zimmert and Seldin in 2019 that derived optimal bounds for the classic multi-arm bandits problem for two different types of loss regimes simultaneously, and we extend their analysis to the problem of decoupled exploration and exploitation in multi-arm bandits. Before showing which results we obtain, let's introduce the problem more formally. We consider a repeated game with K arms. We analyze the performance of the game until a time horizon t, but the learner does not know the value of t. At each round t of the game, the environment picks a loss vector such that the loss of each arm is in the 0-1 interval. Simultaneously, the learner picks an arm AT to exploit and an arm BT to explore. The two arms are allowed to be identical. Then the learner blindly suffers the loss of AT and observes the loss of BT without suffering it. The losses can be generated in different ways. In this work, we consider the oblivious adversarial regime, in which the losses are generated arbitrarily but do not depend on the action taken by our forecaster. We also consider the stochastic regime. There, the losses are drawn according to some fixed distribution. We define the suboptimality gap as the gap between the expected loss of one arm and the expected loss of the best arm, denoted I star. We measure the performance of forecasters in terms of pseudo-regret, which is the difference between its expected cumulative loss and the minimum over the expected cumulative losses of each individual arm. This best arm is identified in hindsight. Now we can introduce our algorithm. It is based on the Tsallis-INF forecaster presented by Zimmert and Seldin. First, we construct the distribution PT. It is from this distribution that we sample the exploitation arm, PT. The construction of PT is based on follow the regularized leader framework with regularization by alpha Tsallis entropy. The parameter alpha is a constant between 0 and 1. Then we compute the exploitation distribution QT. We pick the distribution with minimize our pseudo-regret bound. Next, we sample the arms AT and BT, blindly suffers the loss of AT and observe the loss of BT. Finally, we construct the loss estimators. Those are very simple, unbiased estimates of the true losses. Note that because we observe the loss of arm BT, we need to use the distribution QT in order to construct unbiased loss estimates. We have analyzed the decoupled Tsallis-INF algorithm and derived pseudo-regret bounds in the oblivious adversarial and stochastic regimes. First, in the oblivious adversarial regime, it has been shown by Avner and al. That the lower bound for the decoupled multi-arm bandits problem is the same as for the classic multi-arm bandits problem. Thus, our bound does not only improve on the result of Avner and al., but it is also optimal up to constant factors. The result in the stochastic setting is much more interesting. Here, our result significantly improves on the work of Avner and al. Note that our time-independent bound is also tighter than the lower bound for classic multi-arm bandits. This is possible because the problem of decoupling exploration and exploitation is a simpler problem. We expect that it is possible to refine our bound more, but we know that it is at most suboptimal by a factor k over log k, because in the full information setting, Murtada and Geifas have derived the lower bound in log k over delta min. If you're interested in learning more, the article will be available in the proceedings of COLT this year. Plans for future work include studying the optimality of our results in the stochastic regime and extending our results to other problem settings. In particular, it would be interesting to extend our results to problem of production with limited advice, so problems where the player has access to a subset of the loss vector at each round, because this problem is closely related to the problem of decoupling exploration and exploitation. Finally, here are the articles that we referenced during this talk. Thank you for your attention.